the result will be different if you act at lower point down here. Let's say this thing is a chair. I can apply the same force at this point and at this point. If I apply the force at this point, it rotates clockwise. But if I apply the force at this point, it rotates counterclockwise. Which the location, the exact position that the force is acting on is very important for rotation. And the lever arm should be the distance from the pivot to that point. So take the component, you extend the lever arm, and find this angle theta. So the torque caused by the first force will be R and sine theta. Now, just like applying force at different location will give you different direction of rotation, let's apply the same direction of force here. F2 and F1 has the same direction, but the result in rotation is different. You can see that the lever arm is this one. And if you pull the force in this direction relative to the pivot, it's going to rotate counterclockwise, while F1 rotates the thing clockwise. So we know if we want to describe this difference in direction, we should have a sign difference between torque 1 and torque 2. The formula of the torque is the same as long as you choose the right angle. It's the angle between the lever arm and the force. So they have a sign difference, and usually we choose counterclockwise as positive. F2 is rotating counterclockwise, so let's say this is positive and this is negative. Okay? The key is that in this case, when you add them, it is possible for them to cancel each other. You have minus R1, F1 sin theta 1, plus R2, F2 sin theta 2. The R is lever arm, is the length, is always positive. Force is the magnitude of force, is always positive. This angle will only go from 0 to 180, which is always positive for the sine function. So the only sign difference comes from the direction. As long as you keep track of the direction, you'll be fine. So you see, it is possible for minus plus negative plus positive equals 0. So which means that the torque caused by these two forces cancels each other, so the thing will not rotate. But if they are not equal, then you can see which one has bigger torque. If F1 has bigger torque, then you will end up rotating clockwise. If F2 has bigger torque, you end up rotating counterclockwise. Okay? There are a lot of applications about lever arm. Please review them by yourself. I don't have time to go through all of them. So once it starts rotating, we want to describe the rotational motion. The way we do that is to use this angle theta, which will change with time. If it is rotating this way, this angle will increase with time. Okay? Just like we define velocity, we define angular velocity as the change of angle divided by the change of time. But we know if a thing is rotating and there's no external force acting on it, it will just keep rotating, just like the sun, just like the Earth going around the sun. The speed will not change because the force is perpendicular to the displacement, so the work is 0, and the energy will not change. So we know if there's external torque on this ball, it will change the angular velocity. So we define the change of angular velocity divided by the change of time as angular acceleration, just like how we define acceleration from velocity. Okay? And you can see that if I go for an angle theta, this arc length is going to be r times theta. So the speed will be the distance traveled divided by the change of time, and the change of angle divided by change of time is what we define as angular velocity. So you have v equals r omega. And if you look at the component of acceleration tangent to the circle, I need to emphasize that because the acceleration is not tangent to the circle. Even when the angular velocity is not changing, you will have an acceleration going to the center. And you need to know how to derive that. So the direction of acceleration is this way. But if we just want to look at the tangent component of acceleration, it will be r times alpha. Okay? Any questions so far? So we can apply Newton's law. Say, all right, let me apply a force and make it always perpendicular to the lever arm, so the torque is a constant and everything is easy. Then we have the torque in this case will be just r times f because sine 90 degrees is 1. When they are perpendicular, you just multiply the lever arm with the force. If they are parallel, the torque is 0. Yeah, you cannot rotate the thing if you are pulling away from the pivot or pushing into the pivot. Alright, so this is the torque, but using F equals ma, you know this force is going to cause the tangent acceleration of this ball. And that should be n times r times the angular acceleration. So compare this with this, you get torque equals then multiplied by r. So torque will cause angular acceleration, and we call the proportional constant moment of inertia. In this case, I equals mr squared, but in general, it will be the sum of all mr squared. But the definition of moment of inertia is torque equals I alpha. It's going to be the ratio between the torque and the angular acceleration it causes. It is not just the mass, it is related to a mass and distance. If I want to rotate this object, like this, then every point of this object is like this long away from the pivot. But if I rotate it like this, it will be a lot harder because every mass is far away from the pivot. And when the distance is longer, the moment of inertia will be bigger because it is mr squared. Okay? So let's look at the case with more than one particle. When you have more than one particle rotating, n1, n2, all the way to nn, then the torque will cause a angular acceleration. Let's say that angular acceleration is a constant. So let's say you apply a force like this, so you get a constant torque and constant angular acceleration. Now, if you push with a displacement r theta, then the work you've done is F times R delta theta, which is torque times the change of angle. For a system, all this work should go into the kinetic energy. So as long as we figure out the expression for kinetic energy, we can get the expression for moment of inertia for the system. So let's say you start from rest. After you push for a distance, the kinetic energy increased by 1/2 mv squared plus 1/2 mv squared all the way to the nth particle. So since the work should go into kinetic energy, you get that the torque times the change of angle, and this will be 1/2 m1r1 squared plus m2r2 squared times the change times the angular velocity squared, where I use the formula here. So this work should go into 1/2 the sum of them times omega squared. And if this is on the exam, I will tell you that for constant torque, the torque times the change of angle will be, I will give you that 2 times alpha times the change of angle will be the change of angular velocity squared. Just like if I want you to derive the work, kinetic energy theorem, I will tell you that 2 times acceleration times the change of x will be the change of x velocity squared. Or you may need to know how to derive it. You derive it by the equations for constant acceleration. The position will change like this, and velocity change like that. You use this equation to substitute t with velocity and acceleration, and you can get this. Same for angular one. So here you can swap omega squared, or let's not do that. You can swap the change of angle times alpha. So torque will be I alpha. So alpha will be this. This angle. Alright, so this is I alpha change of